In the previous class, we have seen this for a transistor, how the band diagram and the electric field distribution, other parameters like electric field distribution, and then we have studied the band diagram of PNP transistor. And I asked you to do for yourself for NPN transistor the band diagram. I hope you have all have done that. And then we started deriving this current gain for a transistor, but we could not complete. So let's continue from there. So in this session, we will derive the current gain equation for a transistor. So for this, we will do it for an PNP transistor, and for NPN transistor, you can do it for yourself. Okay. So let's begin with the different current components. So as you can see here in this schematic, that we have basically different current components in a transistor. So whatever we are deriving here is the transistor is in active region. Active region in the sense the emitter and base junction is forward bias and base collector junction is reverse bias, right? So what happens, how the current flows or the carriers flows here. So when you do a forward bias in the emitter base junction, so the holes in the emitter region, they will be injected into the base region, right? And in the base region, the hole will diffuse through and enter into the collector region. And this diffusion, to enhance this diffusion process, we make the base region very thin. It is less than the hole diffusion length. Okay, and then there will be some holes in the base region. They will recombine with the electrons present in the base region, in the base. So we'll lose some of the holes in recombination process within the base itself. And then we have few more current components arising because of this base. So base, there are as the emitter and base junction is forward bias, so there is a chance of electrons also getting injected from N to P. See, in forward bias, holes will get injected from P side to N side, and electrons will get injected from N to P. So this will contribute to a current of IEN. I mean, it's a denotion. So it's a emitter current, IE. It is carried out by electrons. So N suffix for electron. Similarly, IEP is the emitter current, which is carried out by the holes. So IEP, P stands for hole, right? So we all know this nomenclature. And then there is another chance, some electron will again diffuse through the collector region, so which will contribute another current component called ICN. And then there has to be some flow of electron from the battery, because we are having some recombination here. This electrons and holes, they are recombining in the base region. Some of them are recombining. So to supply those electrons, some electron, we have to supply those electrons right in the base region for a continuous flow of current. So for that, battery will help. So that current is determined, denoted by IBB. It's for I current, I in the base. First B is for base and second B for the battery. Okay, so with all together, the transistor works. So let's try to correlate them and derive some parameters for transistor. Okay. So we are basically going to derive the current gain of a transistor. Okay? So it's called current gain. CURRENT, current gain. So before going further, we need to first do some assumptions. Then only all this relation valids. So first one is we assume that there is no generation and recombination in this region. This what is this region? These are depletion region. So in this depletion region, we assume that there is no generation and recombination. So assumption is no generation or recombination in the depletion region. Okay. In the depletion region. Okay. So having said that, now let's see for these holes here in the emitter region. So what happens? Let's do step by step. So first, let's consider this movement of emitter current. So the total emitter current, you can see that we can write down that total emitter current IE will be equals to IEP plus IEN. So IEP is the current coming from, is the largest current, right? This is coming from this whole injection process due to the forward bias. And then IEP is the maximum, not maximum, it's the largest one. The value wise, this will be the largest current. Largest current due to the injection of holes from emitter to base. Okay. Okay. And then what will happen? The most of the holes will reach to the collector, and it will contribute to a current of ICP. But some holes will recombine at base, so that will contribute to a current. Okay, so the difference between these two, like whatever the emitter from emitter side, it is entering into the base IEP minus whatever it is entering to the collector, so ICP. This difference will give you the base recombination current. Okay. And in base there are two other currents, right? We have already discussed. One is IEN, and then we have ICN, right? So IEN is the is basically for this is called injection. So it is basically electron injection. Why it happens? Electron injection from base to emitter. And ICN, it is electron diffusion because it is in reverse bias. This base collector junction is reverse bias, so it is electron diffusion here, right? From base to collector, right? Now you can write down some equation like total emitter current. I already wrote. You give equation number 1, and then you can write similarly total collector current will be ICP coming from the whole diffusion, basically from base to collector, and electron diffusion, that is ICN, right? And then you can apply Kirchhoff's current law, right? So I'll give this equation as equation number 2. Now Kirchhoff's current law, you can easily calculate the base current IB has to be IE minus IC, right? Now, if you put all these parameters, okay, let's do it on the right side. I'll move to this side. So you can go ahead here. So IE, if I write, IE is IEP plus IEN, right? Minus IC, I have two factors. So ICP minus ICN, right? Yeah. And now we define one current gain, common base current gain. So let's define a parameter called alpha 0, which is called common base current gain. So common base term, because we are using this common base configuration, right? Whatever the configuration we are deriving, it is for common base configuration. And then we are defining current gain. So current gain is defined as ICP by IE. So what does it mean? So ICP is the actual current. It is coming from the holes which are getting diffused, which are diffused from base to the collector, right? This contribution ICP, and the total emitter current is IE. So it has to be less than 1, right? IE is always bigger than all the currents. So it's called common base current gain. And now if you put this term, so this will be like ICP, but IE we already defined from equation 1, right? I can write IEP plus IEN, right? So this is the common base current gain expression, and you can write down it further. So ICP by, you can write down as IEP by, okay, I'll tell you why I'm doing this. So IEP plus IEN into, we'll have this ICP, but this IEP I am just multiplying on denominator and numerator, this IEP, this and this, rest all are same. Now this first term is called emitter efficiency. It's called gamma. So the first term gamma is called emitter efficiency. Okay. You can see that emitter efficiency, why it is called emitter efficiency, you can see the number of, or the current because of the hole by total emitter current. We want actually it's to be 1. I mean, we want all the current to be contributed from this hole, not from this leakage current, or the current is coming from the electron contribution, this base, and the injection of electron from base. We want to reduce this IEN. In ideal case, we want this IEN as small as possible to get emitter efficiency unity. So how to reduce IEN? IEN is coming because of the electron injection from base to emitter, some forward bias condition. So to reduce that, what you have to do, you have to change the doping concentration. So you make the P side, you make this P side heavily doped and N side relatively less, then the this majority carriers, whatever the electrons there in the base, the number will be less than the majority carrier present in emitter, that is hole. So you can reduce by using different doping concentration. So that's why you make emitter very highly doped. So you have more number of holes and less electron, comparatively less electron in the base to achieve this gamma to unity. Okay, and then we have this second term which is called base transport factor. It's called base transport factor, alpha T. It's called base transport factor. So as you can see, this term, why it is called base transport factor? Because see, ICP is the current it is transporting, right, from base to collector, and IEP is the how much the holes is getting from emitter, right? I mean, how much is the flow of holes from emitter and how much it is able to transport to the collector. This is basically base transport factor. So if it could transport all the holes without any recombination to the collector, then IEP will be ICP is like 1. So base transport factor is 1. But in practical, it cannot be 1. There will be some recombination loss. So this factor, ICP by IEP, it determines the base transport factor. So how much holes you can transport from emitter to the collector? What's the factor? That's all. So if we write down this two factor, it is like gamma into alpha T. So we have defined these two parameters, emitter efficiency and base transport factor. So finally this will be your alpha 0. We started from here. Alpha 0 is the common base current gain. So alpha 0 is, this is another standard equation. So this is our equation 3. Okay. And now we'll derive this collector current. Okay. So let's do it here. So we'll define now collector current. So collector current is, total collector current is IC. IC is equals to, we have already defined, right, IC? Yes, we defined here. So it's equation 2 again. So it is ICP plus ICN, right? Now we can write down ICP from this equation 3 now. Okay. Here. So alpha 0 we have written, right? This common base current gain is ICP but alpha E. Sorry, IE. So this is the equation number 4 if you define. There's nothing, I'm just taking from here. So this is our common base current gain, it's by definition. Now from here, if I take this ICP will be alpha into alpha naught into IE. So I'll just put this one here. It is alpha naught into IE plus we have ICN, right? Wait a minute. So ICP is, something was wrong. Just a minute, I got a confusion here. So alpha T is, okay. Okay, we can write down with this, or we can write down ICP from here as well, right? So alpha T is equals to ICP by IEP. right? So we'll write down in terms of alpha t. Okay, so let me erase this. So from this equation, ICP will be alpha t into IEP, right? Everything is okay. Okay. And now we know. Okay. Now we just multiply one gamma alpha t IEP by gamma. So we're just multiplying gamma numerator and denominator in the equation plus ICN. So this will give you we already got this actually from this equation, but anyway, they are all linked. So IC we can calculate from here. So IC is equals to this, or we can directly calculate, right? ICP we know here from equation 4 also it is coming, or we can calculate from this alpha t also. I think directly is better. You use equation 4. So in equation 4 we have alpha naught equals to ICP by IE. So you can put this one and directly you can get IC here from equation 4. Right? So this defines the collector current, right? Now ICN is what is ICN? It's the collector base current flowing with the emitter open circuited. So let's define, let me move it here. So I'm trying to define this ICN. ICN, if you see the picture here, ICN is coming because of the electron diffusion from base to collector, and it is nothing to do with emitter. It is because of this reverse bias condition between base to collector. That's why this ICN, right? It's basically the leakage current, the reverse saturation current also you can say, because for electron definitely. Reverse saturation current because of the electron, right? ICN. So we can write down this ICN as ICO. I mean, more precise way of writing ICN to ICBO, because C and B is your collector and base. So it is the current flowing from collector to base, and 0 stand for the third terminal, that is emitter is open. Because for this current we don't need it doesn't have any contribution from emitter part or the emitter base junction, right? So we can write down ICN to ICBO. So it totally depends on the voltage between collector and base. That's why it is coming ICB. And emitter to base, this potentially could be 0. So you can open the emitter terminal, and whatever the current flows from base to the between base and collector is your ICN. Is it clear? So if you consider this, then we can write IC as alpha naught IE plus ICBO. It's the reverse saturation current, basically ICBO. So this is your final collector current. Okay. So any doubts so far? Please, Vikrant. Okay, yes, Vikrant.
Sam, sir, can you repeat that ICBO current?
Which current?
ICBO, sir.
ICBO.
Emitter.
Okay, so ICBO, we are basically replacing this ICN with ICBO, this notation, because it looks more comprehensive. It tells you about the current between collector and base. So ICB, so collector and base, when the emitter is open. 0 stand for the third terminal, that is emitter point is open, because see ICN, you see the figure or how we define the ICN. ICN definition is because of the electron diffusion from okay, so it's minority carrier, so electron diffusion from collector to base, this arrow, this dot dot arrow. So in this figure, this dot dot arrow is the defining the electron flow from collector to base, because they are in reverse bias, this base collector junction. So it's minority carrier diffusion, right? Now, and the current contribution will be opposite direction, right? So that's why ICN is flowing from base to collector, but the flow of electron is collector to base. So, okay, now the notation ICBO, we are just replacing this ICN because we can get the same ICN by opening the emitter. We can imagine the emitter terminal is open and it's just the reverse bias diode current between base to collector. So it's a reverse saturation current by the electron when the emitter terminal is open in this transistor. That's what it means. Is it clear, Vikrant, now? So it depends on basically voltage between collector and base, and emitter terminal is open. This whole three terms means.
Yes, sir.
Okay. So we have defined certain parameters for transistor, right? So let's just recap a little bit. So many parameters we defined. One is our common base current gain, which is alpha naught, is ICP by IE. So physically you have to think, in exam time sometime you may not remember all this terminology, but you remember the concept, like it is common base current gain. And because, okay, it's a current gain, so it has to be ratio of two currents, and it's a gain. So it is defined by the total emitter current with respect to the current which you are collecting at the collector side. So ICP, basically ICP is our final, or the current we get at the output, you can imagine, and IE is our input emitter current. So the ratio between two will give you common base current gain, and definitely it will be less than 1, because IE is always greater than, IE is sum of this IB and IC, so it will be less than 1. And then we define another parameter called emitter efficiency. So emitter efficiency is the total emitter current is in the denominator, right? And the numerator we have the current because of the holes. So we want this IEP maximum. I mean, IEP should be equal to IE. We want very little of this electron contribution from base. This IEN want less. So this is how your emitter efficiency, and then we define another parameter is base transport factor. Now base transport factor is the current ratio of whatever the current it is able to deliver to the collector with respect to how much the current it is receiving from emitter. It's very obvious, right? So it is ICP by IEP. Now for an ideal transistor, we want this base transport factor to be 1. We don't want any recombination loss in the base. Now to reduce this recombination loss, that's why in the physical transistor you will see the base is very, very thin compared to emitter and collector region. And the thickness is determined by the diffusion length of the hole or the electron if it is NPN transistor. And it has to be less than the diffusion length of the carrier. Otherwise they will recombine, right? So to reduce the recombination loss, we minimize the base dimension. Okay. Now let's move on another carrier distribution in each region. So we know now the current contribution from each region, how the current flows in a transistor when it is in active mode for an NPN. So for an PNP. Now for NPN transistor, you can do it for yourself as a homework. For NPN transistor, you can derive all this. Nothing, it's just replace holes with the electron, this notation, and of course your current direction will change because that time here the hole is the main current carrier, but in NPN transistor the electron will be the main current carrier within the device. So electron flows, the direction the electron flows and the direction current flows is other way around, so you have to be careful. It's the same, but we have to take care of the direction when you talk about flow of electrons. So you try to do it for NPN transistor for these derivations. Okay, and now we'll move on and derive this carrier distribution in each region. Okay, so we're going to derive now carrier. We have already done for diode, right? PN junction. Before going further, so we need to have the concept of continuity equation. Again, so all this, whenever you talk about carrier distribution for any semiconductor devices, you have to bring into this continuity equation concepts. So for PN junction, we have already derived, right, how these minority carriers or the majority carriers, electrons and hole, they vary across the device. Now we'll do it for transistor. It's very similar, but we have different boundary conditions for a transistor, and we can do it. So for continuity equation, let me bring all those not boundary conditions, some assumptions we do, right? So first assumption is the doping. So we need uniform doping. Otherwise, I mean, if the doping is not uniform, then it will be very complicated, right? All the equations and all we derive. We think that doping concentration is uniform throughout the region. Let's say emitter, throughout the emitter, the doping concentration is same. Throughout the base, doping concentration is same, and similar for collector. But they could vary region to region, right? Base will have moderate doping, right? And emitter will have the highest doping concentration. That's fine. But within the collector, within the base, within the emitter, the doping concentration is uniform. That's what it means. And then the whole drift current in the base region as well as the collector saturation current is negligible. So why you are assuming this? Whole drift current in the base region as well as the collector saturation current is negligible. See, in the last equation, last derivation, if you notice carefully, let me go back. So we didn't consider, no, here we have considered everything. So whole drift, yes. sorry, hole injection of hole, injection of electron, and then here hole diffusion, electron diffusion. Yeah, in this we consider everything, right? But for this carrier distribution formalism, we will assume that this whole diffusion current is 0 in the base region. Whole drift, sorry, whole drift, only diffusion current. We'll get into those when we derive the equation, and then we have again the another assumption we do, that is low level of injection, and then there is no generation and recombination happening in the depletion regions, and there is no series resistance for the device. So these are the 5 assumptions. It is there very much in the our textbook, so I'm not writing down here. So these 5 conditions first has to be, I mean, these are all assumptions, and then let's derive for the base region first. So we have 3 regions here. In the PN junction, we had just P and N type. Now we have 3 regions. So for base region, now we are considering here the transistor is PNP, right? We are deriving for PNP transistor. Okay, these are not in dimension, these regions. In fact, it is base is more wide here, but don't worry, it's not in dimension, just a schematic. So in this, if you write down the continuity equation for holes, so how we can write down? So if you remember, the continuity equation is dP equal to d2p n dx2 minus pn minus pno by tau equals to 0, tau p, right? So this is the continuity equation for holes in the base region. So this is for the base region, because in the base region the minority carriers are holes, right? And you can write it in this formula because of the steady state condition. So here the conditions are, again, the electric field is 0, and then steady state steady state flow. So all these assumptions are there as we have used in our continuity equations. Now here what is happening, whatever the holes, they are getting injected from P region to N side, and then they will diffuse in the N region and enter into the collector basically. So this is the continuity equation, and this the second parameter, you know, right? This is our recombination rate basically. Recombination rate. We had few more terms like generation rate, that is 0, because we are considering there is no generation in this transistor, right? And no electric field. Now with this, if you do the again solution of this equation, so earlier we have done this solution, right, for this continuity equation. Some of you have already solved it, so I'll just remind you the solution once. You have already done for yourself. So the solution was like Pnx was equals to Pno plus Pno plus, sorry, minus Pno into e to the power minus x over Lp. because we got this solution with some boundary condition, right? We had boundary condition like Pn at x equals to 0, it was PNO, and Pn at x equals to infinity, it was the PNO. So with this boundary condition, we derived this. Now, if you solve this in more general solution, will be Pn at x equals to 0. Sorry, not x equals to 0. Pnx. We're writing more general, so Pn plus C1 to the power x over Lp plus C2 to the power minus x over Lp. So this is most general solution, but if you use this boundary condition like we used in the last section, then we got this particular solution. And this one, the last equation, it is most general solution for this continuity equation. Now here this C1 and C2, this constant, as you can, if you compare this with our last solution, then you'll see this C1 and C2, they basically depend on the boundary conditions, right? So for a transistor, if you if you take the boundary conditions as, so let me write down the boundary conditions for transistor. Okay. So this one, whatever I'm defining here, don't get confused. This one, this part, whatever I told this within this circle, not circle, within this boundary, this is just a recap for PN junction diode. Okay. And now we are going back to transistor again. So for a transistor, the boundary conditions will be different for sure. So this, let me write down the boundary conditions for transistor, and then we'll see. So PNO has to be equals to PNO e to the power Q V EB by KT, and PNW is equals to 0. So to understand this, let me draw the schematic. Otherwise, it has no meaning. What is W? What is 0? Okay. So let me draw the transistor. So this dotted within this region is our, okay, let's write down. So this is emitter, base, and collector. So this is the, within this dotted region, this region is the depletion region between emitter and base. And then we have another depletion region, right? It's much wider because of reverse bias. So this is the depletion region between base and collector. Okay. Now we'll define some boundary conditions. So we are starting from 0 is here. So this is our X. 0 is here, and this is the W, the base width, basically the neutral. So this, whatever the unshaded area, those are the neutral region, right? Like this region in the emitter, these are the neutral region of emitter. This is the neutral region of base, and this is the neutral region of the collector. The shaded region are the depletion region, and they are ionized basically, right? So we have all donor acceptor ions here. And we define another two. So this is Xc and this is X minus Xc. So this is basically the boundary of depletion region in the emitter side, and this Xc defines the boundary region in the collector side. And 0 to W is the neutral base region width. Okay. Now coming to P and O. So you are in the base region. Okay. So this P and O, okay, is the, so 0 is here. So P and O defines the hole concentration. Yeah. So it's the hole concentration at X equal to 0. And of course, this is in the N region. So P and O, P is for, this is for the hole. N is our N type, right? So here we have P and O. So we'll have maximum hole concentration at this boundary, right? So most of the holes, they are getting injected, right? They are getting injected from emitter to the base. So at the entrance point of the base, we'll have maximum hole concentration, and then they will, the concentration will reduce, right? Because of the diffusion. So they will diffuse, and then and they are related by this equation, and this equation we already studied. Pno equals to Pn0 into e to the power q. Okay, so here we are writing VBE because the base and emitter voltage, we are considering about this region, base region. So we are writing this VBE, and this equation is well known, I think, for all of you. We have derived this equation, how this concentration of holes or electron, they fall off with electric under potential bias, right? And P and W at here, it will be 0, right? So now with this boundary condition, if you solve, you will get a big equation. I will refer to this in the book, and I will ask you to solve this. I will not do in the class. It will be a big mathematical solution. I'll request all of you to try this solution. So for continuity equation, we solved this equation by using this, for PN junction diode, we solved this continuity equation with the help of these two conditions. Now you can solve the same continuity equation with these two boundary conditions. So this is our boundary condition 1, and this is boundary condition 2. So with these two boundary condition, you can solve this continuity equation. Let's say it is equation number 6. So you can solve this equation 6 with these two boundary conditions, BC1 and BC2. Try to solve this. I'd also try. I have not tried yet, but let's solve this equation and see. Okay. So we'll meet in the next class, 9:50. Okay, we'll meet in the next class. Hope some of you could solve this equation and follow the book for the final equation and expression. I'm not writing it; it's too big. You just follow the textbook, this Z book, and try to solve it. And next Monday we can have a discussion. Next session we can have a discussion. Okay.